one of the methods that we can use to find a determinant for a matrix, instead of looking at the diagonals and coming up with a bunch of products and then summing those together, is we can use something that's called the cofactor expansion. And we're going to look at a definition first to get an idea of the terminology and some of the symbols, and then we will look at a example matrix and how that compares information-wise to this definition. So looking at the definition, we see that the minor of an element, in this case we're just calling it little d and its index ij, that is telling you that the position that it lives in inside the matrix. So an element 1, 1 would be in the uppermost left-hand corner. That would be the row 1, column 1 position. So that's what the little index ij is standing for. We also note that this is for square matrices only. We're not doing this for any rectangular matrix. It's specifically a square matrix, so an n by n matrix. We're going to call our matrix D in this situation, and then the minor is actually going to be denoted with an M, and then the same subscript, the indices that we used on the element itself that we're interested in. So we're looking at the minor being subscripted ij. And then this minor is going to be defined to be the determinant of the submatrix that remains when we remove the ith and the jth row and column from that matrix that line up with their intersection at element D with that subscript ij, whichever element D that we had chosen. And that is going to give us kind of a smaller matrix once we eliminate everything from the row and column that element is in, and we make this little matrix and take the determinant of that. We also have to kind of have this adjustment factor of a -1 or a +1 that multiplies by each of these little matrices, these submatrices that we have created. And this adjustment factor along with this determinant is going to be called a cofactor, and that cofactor is in respect to the element that we have chosen. As an example matrix, we are going to let D be the 3 by 3 matrix with the entries 1, 3, 0, 9, 5, 2, 3, 2, 2. Now, going to our definition, we had element D sub ij was some element in the matrix. For our example, I want to focus just now on the element of focus being D sub 1, 2, which will be the first row, the top row there, and then the middle column, and that will be element 3. You see 3 in that position. If we strike out the top row, row 1, and we strike out the second column there, we see the intersection of those two strikeouts is the element 3, and the elements 9, 2, 3, 2 are still visible to us. That's going to be the matrix that we want to find a determinant for. We are going to make that our submatrix with the entries 9, 2, 3, 2, and we will find the determinant of that. We also have to have this adjustment factor of the -1 to some power, and that's the I plus j power. So 1 plus 2 is 3, -1 to the third power will give us back -1. So our cofactor is going to have a -1 times whatever the determinant value turns out to be. Having discussed that, I now want to state a theorem, and our index for the I and j are going to run from 1 to n. Since we are talking specifically about square matrices, n is going to be the number of rows and the number of columns, and that number is going to match. We're going to let the index I and j run from 1 to n so that we pick up all of those elements in the square matrix. And then we are going to pick a row or a column to be our focus. It will work either way. And you see there's two different sums of products stated in this theorem, and that depends on whether you chose a row or a column to focus on, but we are going to choose the entire row or the entire column. We're going to create these cofactors and multiply the elements that those cofactors are derived in respect to from our definition. And the sum of the products of an entire row or an entire column is actually going to be the determinant for the matrix that we're working with. And notice this is not specific to the 3x3 matrix. I'm just using the 3x3 matrix as my example. This is for any square matrix. So this works for your 2x2 up through your 5x5, 10x10, 100x100. This theorem is working for any of the square matrices. Bringing everything that we've discussed together, the definition, all these little parts that we've talked about, and my example 3x3 matrix, we are going to look at finding the determinant now for the example 3x3 matrix. So we're just going to choose the top row here, and we are going to pull out these submatrices for each of these. In our example, we're going to use the top row, and we're going to pull out all the submatrices based on that top row. So if you look at position 1, 1, that has the number 1 in there, we're going to multiply that by -1 to the 1 plus 1 power. And if we cross out the top row and the first column, we're left with 5, 2, 2, 2 as our submatrix. So that's going to be the submatrix that we find the determinant of. To that, we're going to add the second number in the first row times -1 to the 1 plus 2 power. And then we're going to multiply that by the submatrix that we get from eliminating the row and the column containing that number 3. So again, we get 9, 2, 3, 2. And then lastly, we're going to add to that the 0, and it's going to be times -1 to the 1 plus 3 power. And when we eliminate the top row and the last column, we have 9, 5, 3, 2 as our sub matrix. At this point, I kind of wanted to just put 0 in here for this last term because that's what it's going to come out to be. Since we have a product containing 0, we know that last term is going to 0. That actually leads us to a tip to get us through a calculation like this faster. If you have a row or a column containing 0 and you're using this technique to find a determinant, you definitely want to pick that row or column containing 0 because it's going to just simplify your calculations. As we start to simplify this, we see that determinant D for our matrix D here is going to be these things as we begin to simplify them. The first step that I've gone through is I've begun to do the determinant by definition. So you see I've got all my subtractions in here where I found the product of the diagonals and now I'm subtracting them. We also have to clean up these -1s so that we either get a +1 or -1. Anything where the sum is an even number gives us back a +1. Anything with an exponent of the odd numbers giving us back that -1. And then we just run through those products and then we add or subtract as we have them. And in this case, we come out with -30 being the determinant for matrix D. And that's something we have to keep in mind, that these don't always come out to be positive numbers. You also can get 0 as a determinant, and you can get 1 as a determinant. If we get 0 as a determinant, that's super important because that lets us know that this matrix that we're working with is not going to be invertible. So that's critical to recognize, that when you get the determinant of 0, we're not going to be able to find an inverse to this matrix. If this is part of solving some system of linear equations, then there's going to be some issues here because you can't have an inverse, and so you can't proceed. And you have to know how to interpret that 0 in the context of your system of linear equations. Hopefully this has been an interesting video for you. Cheerful calculations.